Camps on everyone. Let's start off. So last class we have finished with the Pascal's law. Today we'll be starting off with the bind force. Hope everyone has gone through the notes. Great. Let's start off. Others, do keep your camps on. So what is this bind force? Like last time I was saying, Archimedes figured out something when he was in this bathtub. So what was that he thought of? So when a body is immersed in a fluid, it experiences an upward thrust. Which is equal to the weight of the liquid displaced. So how did we get this statement exactly? So this is what Archimedes says. You consider it's a thought experiment, meaning you're just arguing with this argument there. Let's say there is a liquid here. Then Archimedes says, okay, consider an imaginary closed surface. It could be anything. We could have taken a cube also. Right now, if you see in this, the molecules are entering, molecules are leaving outside, but at any point of time, the amount of liquid inside this thing is constant. Again, remember, it is just your imagination. You just imagined some dotted line, some closed surface, and you're saying it is at rest. So amount of liquid inside is constant. Then Archimedes says, okay, great. Now, if you try to draw the FBD of this liquid, and if you look at the forces, one thing is clear, there is a force mg, which is density of the liquid, volume of the liquid into g, right? That is there. Now, this is the Archimedes argument. Tell me one thing, if I take a block, and if it has some weight, and if I leave it, what will happen? It will just fall down, right? Now, Archimedes says, but boss, this liquid here, which I imagined, is not falling down. Getting it? It is not falling down. That means there is someone there who is balancing the force. Now, who is that? I don't know. You're getting the thing? We don't know who is there, but the argument was this. So it was supposed to fall, but it is not falling. That means there is someone there. And now who else is there? Tell me thing, like who can possibly exert force on this thing, on this imaginary thing? There is only one guy who is there. That is the surrounding liquid, isn't it? So he said, okay, the only other person or the only other thing that exists here is the liquid. So this surrounding liquid is somehow exerting a force in the upward direction, which is balancing the weight. Now, Archimedes didn't have a proof for this. Are you getting this? This is completely experimental. It's like, I keep giving that example, right? If you have two cakes in the fridge, mom goes out and your sister eats both the cakes. And when she comes out, both the cakes are missing, right? And you have not eaten it. We know your sister has eaten both the cakes, even though you don't have the proof. Something of that sort. Getting it? Now, this is what we call as bind force. So technically speaking, if you actually ask Archimedes, boss, what is buoyant force exactly? He will say, I have no idea. You're getting it? I have no idea what is buoyant force. And you need to understand one thing. The reason why we respect this guy so much is because this was some 2000 years back when people didn't even have a concept of force, right? There was not much of a science. And this guy was able to figure out so much with that argument. So that is one of the reason, right? It is, he was like, so considered. So this V is the volume of that imaginary body there. Fair enough. So from argument here, the force due to the surrounding liquid must be equal to mg because it is in equilibrium. This is what we call as buoyant force, which is density of the liquid, volume of the body, or volume of the volume displaced into G. And that's it. That is the only new thing we are going to learn today, and we are going to play with this. Let's write a few more details about it. But everyone clear with this argument here? Clear? Now, then Archimedes says, okay, fair enough. So we got the buoyant force. Now, what if I replace this with a solid? If we replace the imaginary thing, now you tell me, does the surrounding liquid know what is there inside? This is what Archimedes' argument was. This was the surrounding thing. Somehow the surrounding liquid is pushing this surface, right? So that means the surrounding liquid has a problem with the surface, but not exactly what is inside, isn't it? Inside you could have kept water, you could have kept gold, you could have kept soil, you could have kept anything. Why will the surrounding liquid exert different force? Because the material inside is different, even though the outside surface is same. Meaning, if I give you 1 liter ka Amul milk packet, that that carton box, and inside if you put oil or if you put water, can you tell what is there inside just by seeing outside? It doesn't make a difference, right? Outside it looks the same. So his argument is the surrounding liquid will still exert the same force. So the buoyant force doesn't care what is the material made of. So the buoyant force will still be rho L V G. This would be mg. So this would be rho body Vg. Now, if density of the liquid becomes greater than density of the body, that means the buoyant force will become more. This will float. If density of the liquid becomes density of this thing, then it will sink. So this argument, right, that heavier objects sink and lighter objects float. So people used to think like this. If something is heavy, it will sink. Even now, also we think sometimes like that. But if you actually take an elephant and you take a rat and throw them in the water, elephant actually floats. Elephants are pretty good swimmers. Rats will actually die because elephant, right, is mostly made of fat and all. Right, it is less denser. It actually easily floats. Even same thing with where if you fall into the water, right, and you don't know how to swim, one way to survive, right, is to take a deep breath, hold it, right. When you hold it, this is what will happen. Your lungs are filled with air, your overall density actually decreases. Understand one thing, humans are still made of water. Most of it is water. So by taking a deep breath and filling your lungs with more air, your lungs will actually act like airbags. You won't completely float, but if you are calm, the most people die because they become scared, they start drinking water, the lungs get filled and then they're gone. But if you can somehow stay calm, take a deep breath, fill your lungs with air, then what will happen, right? Most of your body will be down. Your face ka some part can be up. Meaning this is kind of, I'm drawing pretty bad, but there. I don't know. This is not human, but he can. So what will happen is, you can just put your mouth and the nose outside the water. That much you can do. And then what you do, don't leave all the air out. You have to take small, small breaths. You have to maintain that air in the lungs. You will actually float. Getting it? And then if you take a dead body, right? And if you actually throw in the water, it's a very bad idea. You will get caught. So when you throw the dead body initially, it will fall, it will sink. But after a day or so, it will float again. You know why? Because once the Atma leaves the body becomes lighter and then it floats. What do you think? So what actually happens, right? Once you throw that body or whatever, a dead animal, right? The body starts decomposing. In this process, it starts releasing methane gas. So the body actually becomes bloated and it is filled with gas. It becomes less denser, body floats. So that way, even if you have a dead fish or something, initially it will sink, but after a few days, it will start floating. So if the logic is that heavier objects sink, then shouldn't these ships which are made of metal should sink? But they float. So the reason is this: the metal and the ships are actually made of a lot of empty spaces. The average density of the ship, the metal plus the compartments, is actually less than water, much, much less than water. You're getting it? So what decides something will float or sink is not the mass or the weight, but the density, the average density. Clear with that? Keep that in mind. Great. So great. So Archimedes didn't know what it is, but we have an idea. So what is this exactly bind force then? So bind force is actually is due to difference in pressure between upper and the lower surfaces. Right. So that means if you actually take a body, you will notice as you go deeper, the pressure increases. Now, Archimedes didn't have an idea about this. So the pressure is less here. But as you go down, you can see the arrows are becoming bigger. So pressure is more. Then this pressure is less on the top. So there is a force due to the lower surface, and then there is a force due to the upper surface. So what we figured out is the force on this lower surface minus upper surface is actually bind force. So bind force is not actually some new kind of force. You're getting it? So technically, if you ask what is bind force, first of all, bind force doesn't exist. You're getting it? It is actually a fictitious force. Even if fictitious force, meaning it is not a real force. Archimedes didn't know about pressure, right? So he started calling this as a bind force. Technically, he's not wrong, but so if you ask me, right, bind force is an experimentally derived thing, whereas pressure is a theoretical concept. Think of like this: if you have 1 lakh in the bank and you wrote a check of 1 lakh for the same amount, how much money do you have? 1 lakh only, right? Do you have 2 lakhs suddenly? If you want to keep the money in the bank, don't use the check. If you want to use the check, the money in the bank will go off. You can have only one of them. Are you getting it? It is the same amount of money. In one form, you are saying there's a bank balance, in one form, you are saying it's a check there. Getting it? So this is an important statement, everyone. While drawing an FBD, either use pressure or use bind force. You cannot use both of them because both are one and the same. Pressure or bind force, but not both. So pressure is a theoretical quantity. Meaning, if you see from the starting, right, pressure we defined. Pressure is coming like this, pressure is due to that, and we wrote it on a paper and we proved what is pressure. Whereas bind force is completely experimentally figured out. So pressure is theoretical and bind force is experimental, but you're talking about the same thing. Are you getting this? So both are not two different things. Let me give you an example. But are you guys getting an idea there? So the thing is, Archimedes didn't have an idea about pressure and stuff. So he's called this force buoyant force. Whereas fundamentally, if you actually go and look at it, it is nothing but the force due to the pressure. So you cannot use both of them in the FBD. Let me show you with an example. So we have a container filled with liquid. We have a cube here of psi L. Density of the body is rho b. Density of the liquid is rho L. So X part of this thing is inside the liquid. X is the depth of the block inside liquid. So I want to find X. Now let's try to do with the both the FBD. So first FBD is FBD with buoyant force. So the moment you say buoyant force, don't even talk about pressure anywhere. You should not talk about any pressure. So the diagram would look like this. This is the cube. This part is filled with liquid. This was X. This was L. This was L. So buoyant force is the weight of the liquid displaced. So density of the liquid. How much this liquid is displaced? X into L square. The red shaded area is the liquid displaced into G. You have your own weight mg, which is density of the body, whole volume L cube into G. Equate them. Since it is in stable equilibrium, FB is equal to mg. So the game is still equilibriums only. So rho liquid L square xg is equal to rho b L cube G. So we get X is equal to rho b L by rho liquid. Got it? Now the same thing, let's try to solve with pressure. Now the moment you use the word pressure, don't talk about buoyant force. So this part is X inside. So from the top, you have atmosphere, which is P naught into L square. From the bottom, the pressure will be P naught. So liquid is still here, plus rho liquid Gx into L square. And then you have your own weight mg. So if I try to equate this, we'll get P naught plus rho liquid Gx into L square minus P naught into L square is equal to mg. If you actually notice, this whole term is nothing but the buoyant force. And what is this term here? This term here is actually force due to liquid. This is another important thing. Most people think the force due to liquid and buoyant force are same. They're not same. They're completely two different concepts. So if you subtract this, P naught will cancel. You'll end up with rho L G L square X is equal to rho B L cube G. You get X is equal to rho B by rho L into L. Same answer. So what the mistake some people do, they put the buoyant force also, they put the pressure also, and they get confused. Basically, you're talking about the same thing. You can't do that. You can't have both of them at the same time. And this also gives you an important thing here. So force due to liquid and the buoyant force are not same. Sometimes they can be equal, but you're not talking about the same thing. Force due to liquid, this is the kind of thing they'll ask you in advance. They'll ask you force due to liquid, people will write buoyant force and come. We will see some problems on that. Need not be same as buoyant force. Yeah, in this case, this guy is the force due to liquid. P naught plus rho L Gx into L square. Whereas the buoyant force is something else. Have a look at this example. Clear? Now, I'll tell you what is happening. See, think of this analogy, okay? Let's say person A is there, person B is there, and let's say you're donating some money. Now A says, Are yaar, I'm busy, take this 100 rupees and donate. And B adds his own 50 rupees and donates total 150 rupees. Now what Archimedes says is, Archimedes will say A donated 100 rupees, B donated 50 rupees. What Newton says is, A donated nothing, B donated 150 rupees. You're getting the difference? Newton will say, boss, I don't care about all these indirect effects. I will see only the net effect, direct effect. It's like this. If I throw a book on you and the book hits you, who is hitting you? Making sense? Archimedes being a practical person, he will say, Arun, you are hitting everyone. Newton being a practical, FBD person, he will say, boss, the book is hitting you. You're getting the difference? Both are not wrong, but Newton ka FBD, right? It only talks about the direct forces on the system. It doesn't care how did you get, what is the experiment and all that. So this is what is actually happening. Archimedes says A donated 100, Newton says A gave nothing. Because Newton will only see the net effect, the direct effect, the B has given 150 rupees. Making sense? It's like that only. If I like, it's like me throwing a book on you. Archimedes says I'm hitting you. Newton says the book is hitting you. I hope everyone is clear with this. So there are two main points here. One, while drawing an FBD, if you're using buoyant force, don't talk about pressure and vice versa. Second, force due to liquid is something else. Buoyant force is something else. They both need not be equal. Clear with this. They are the two main points there. Let's say there are a few more points there. So this buoyant force is always upward. And again, the idea comes what is up and down, the direction opposite to the net force. Last time we discussed this, the direction of net force is down. The second thing, so where does this buoyant force exactly act? So buoyant force acts on center of mass of the displaced liquid. So whichever liquid you displaced, uska center of mass mein. So for example, we have a liquid like this, and let's say we have a rod like this. So some of the rod is inside the water. So if you see here, the green shaded part here, this is the immersed part. So the buoyant force will act here, the center of this part. This is called center of buoyancy, COB. Whereas the mg, right, will act on the center of mass of the rod. Is that making sense? If I had to give you one more example, imagine we have a rod here, x is equal to 0, x is equal to L, lambda is equal to lambda naught x. Anyone remember where is the center of mass for this? For a linear varying rod, where is the center of mass? This is the first or second question we did. 12 by 3, if you remember. So you'll get the center of mass at 12 by 3 comma 0 is your center of mass. So mg will actually act there. Whereas the liquid doesn't care what kind of rod did you immerse. The buoyant force will act on the center of the rod. This is L by 2 comma 0. This is your center of buoyancy. Is that making sense? So whatever the liquid you displaced, that means if I take a solid sphere with a cavity and if you immerse this in a liquid, the buoyant force will still act on the center of the sphere because it will displace a full sphere, right? Whereas the mg won't be at the center, it will be shifted a bit. So this is one more thing. So where does the buoyant force act? So first thing is how much will it act? Second thing is where does it act? Right? Then this is one part. Second thing, now this is where the problem comes with the Archimedes thing. Like I said, it's completely experimental. Now in real life, what happens whenever you take a block, the surfaces are not exactly smooth. So bottom surfaces have gaps where liquid is filled. So when you fill up this with liquid, so there is a force due to the lower surface. There is a force due to the upper surface. There is also the force due to the sides. This is how it will be. So the net force, there will be a buoyant force here. But what if the bottom surface is exactly flat? Or let's say someone kept some Fevicol or some gum right on the floor and then you stick the block. Means what you did, you made sure there are no spaces at the bottom. There are no spaces. Now, you can't get a perfectly smooth surface, but one way to do this is you can take some gum or something, right? Put the entire bottom with the gum and then just stick it to the floor. So you make sure there are no gaps. Now, if you see the forces, so the liquid is pushing you from the top, liquid is pushing you from the side, sides will cancel by symmetry. There is no upward force here. There is no upward force here. Buoyant force is not applicable. You have to use pressure to solve. There, these are the cases where buoyant force fails. There was a question like this. They said it is a cylinder is kept some glue and all. It was stuck and the glue started melting because of water. The question was after what time will it, lift off or something like that. So if I had to give you a case example, say it's like this. Let's say we have a container with a hole and someone plugged this hole with a cylinder like this. There, you close the cylinder like this. So the cylinder is blocking the liquid from leaking out. Now, if you look at the forces here, here the liquid is pushing down, fair enough. This liquid is pushing from the side, great. But the problem here is outside it is not liquid anymore. This is some other pressure P naught. You can't use buoyant force. So we can make a general statement. If the lower surface is not covered with liquid, you can't use buoyant force. Upper surface is fine. If it is not covered with liquid also, that will work. But the lower surface has to be covered with liquid. Again, this is not a concept or something, but when you see few problems, you will get the hang of it. You will realize like, boss, whenever the lower surface, there is no liquid, it doesn't make sense. Because the whole buoyant force you defined as the force on the lower minus upper surface. And if lower surface may liquid or anyone, no one is exerting force, only you are gone. If lower surface is not covered in liquid, or fluid. When I say fluid again, air or something, there should be the same liquid there. Generally, buoyant force doesn't work. So there is no one perfect statement there. That's why I gave examples. So when you see these kind of questions, you can be sure, boss, it doesn't work. There is no lower force. Because in this example, if you see outside, the pressure became constant, P naught. Whereas technically, the pressure should keep on increasing. That didn't happen here. Here, the pressure was increasing in the liquid. I think these two examples are sufficient. If you know, right, if this was stuck here, or if the lower surface, if you did something like this, you can be 100% sure buoyant force is not applicable. Go back to the pressure method. There, these are all the main points in this. Again, I'll brief it up. The first one was a definition directly, the weight of the liquid displaced. This we explained by saying, take an imaginary surface, the weight has to be balanced by the surrounding liquid and blah, blah, blah. That was fine. The second thing was this. The buoyant force is nothing but the difference in pressure between upper and lower surfaces. So if you use buoyant force, don't use pressure. If you use pressure, don't use buoyant force. That is point one, right? So pressure and buoyant force are one and the same. One is theoretical, one is experimental. Second thing, force due to liquid is not same as buoyant force. Force due to liquid is actually Newton laws from it comes from there, the direct force, whereas buoyant force is experimental. Third, buoyant force will act always opposite to the net force. The net force you have to include pseudo force. Remember, we did that in the beginning. Fourth point, buoyant force acts on center of buoyancy, which is the weight of the center of mass of the liquid, displaced liquid. Fifth point, if the bottom surface is there is no liquid, right, or if the bottom part is exposed like this to atmosphere, you can't use buoyant force. Clear with this stuff. These are the things. Once you know this, then the entire thing becomes just exactly equilibrium problems. Any doubt so far? Anything you're not convinced? Please ask. Clear? Let's see a question. We have a liquid here. We have a cube. Sidal density is rho b. Liquid is rho l. This part is x, which we just now calculated. Now what you did, first one, container is accelerated up. Second case, container is accelerated horizontally. Gravity is there. Find nu x. Rho l is the density of the liquid. What is the answer? Hmm. Let's see. Now, you need to ask yourself when you draw the FBD, right? Now, if the system is accelerating up with A, right, what happens to G effective? G effective will become A plus G. The same thing, if it accelerates horizontally with A, then your G effective becomes like this, which is root over A square plus G square. And we have seen this before, the liquid actually becomes like this, perpendicular to this guy. That means now the block will float like this. And now when you try to draw the FBD, you will realize the bind force will be rho L x L square G effective. Mass also become mg effective. So Fp is equal to mg effective. This would be rho L xl square. G effective, this is rho B L cube. G effective won't matter, it will cancel out. It remains same. Both the cases it will remain same. The only difference will be in the second case, the liquid will be tilted. So this is independent of acceleration. You accelerate up or down, right, doesn't matter. It will matter in one situation. If you're going down with G, then what will happen? It will become gravity free space. So that is one exception there, but normally it doesn't matter. Clear? Easy? Any doubts on this? So G effective won't matter. It will cancel on both the sides. The bind force will increase, mg also will increase, but they'll increase by the same factor. They'll cancel out. Next one. Clear na? Parth, Nikhil, Devika, Sharman, Arya. Next one. We have a container fully filled with liquid. So in one, you kept a pendulum here of density 3 rho. Another one is another pendulum of density rho. Density of the liquid is 2 rho. Initially, system is at rest. This tension was T1, this tension was T2. So 3 rho is trying to sink and rho is trying to float. First question. If system accelerates up, what happens to T1, T2? I'm not asking between T1 and T2. What happens to T1, T2? T1, T2 will increase, T1, T2 will decrease, T1 will increase, T2 will decrease, T1 will decrease, T2 will increase. ऐसा 4 options होगा और T1, T2 will remain same. So this is before and after accelerating. Second, if system accelerates horizontally, then how will the pendulums look like? Will they go to the right? Both will go to the left. One will go right, one will go left. कैसा दिखेगा? If the system accelerates horizontally, draw the position of the pendulums. Meaning, example, no options will be like this. Yes, there will be 4 options like this. You have to choose one. Yeah, then we got a minute. Let's see. T1 will increase, T2 will increase, T1 decreases, T2 decreases. Others answers. Only two answers are there. That is wrong. Johan, you are right. Abhinav, you didn't answer the A part, you're answering the B part. What is the use? Oh, nahi, Ansh, that is wrong. Let's see. Yeah, that is wrong. Let's see the FBD. No, for this row thing, when I draw the FBD, we have T2, your weight mg, which is rho vg. The bind force will be 2 rho vg. So we can see T2 will be rho vg. In the second case, 3 rho 1, that thing is T1. This thing is m dash g is 3 rho vg. The bind force will be 2 rho vg. So actually, if you see T1, T2 will come the same value. So now, if it accelerates up, G becomes G effective, which becomes G plus A. Therefore, T1, T2 both increase. Now you might think like, yeah, in the previous thing, it didn't matter. Why did it increase now? In the previous one, the difference was this. Listen to this thing. Let's say if I have a body here, if you're applying force 10 here and force applying 10 here, okay? If I double this and if I double this, is there any difference? But suppose if this was 10 and this was 9, if I double this and if I double this, is there a difference now? The difference also doubled, right? You're getting the catch? If the system is already in equilibrium because of or by itself, then it won't matter. But here the tension is coming because of the difference in forces. And when you multiply it, when you increase it, so the difference also increases. Are you getting this? It's an unbalanced forces. One is 10 and one is 9. And if you double both of them, the difference also will double. I hope you're getting it. So both the cases it will increase. And what about the second thing? So if the system accelerates horizontally, what is the direction of gravity? G effective. If the system accelerates A this way, then your G effective is this way. Now you tell me, denser objects will sink and lighter objects will float, isn't it? So 3 rho is denser. So it should sink. So the ball becomes like this. This will go towards gravity. Whereas the lighter objects will go opposite to the gravity. Isn't that what happens normally? When you put a thermocol in the water, why does it go up? Lighter objects float, denser objects sink. But when you say float and sink, you're talking what? In the direction of net force. Is that making sense? This is how it will look. The green one will come towards right and this thing. Think about it in a washing machine when you're washing clothes. Where does the soap ka foam go? Where does the soap ka foam accumulate? Where do the clothes go? Clothes which are heavier will go to the edge of the washing machine, right? Whereas the soap ka foam will accumulate in the center. Why? When a washing machine is rotating, the centrifugal force is away from the center. So in a washing machine, down is away from the center. This is down. Away from center is down. So the heavier objects go away from the center, whereas the lighter objects come toward the center. So the soap ka foam accumulates in the center. Is that making sense, everyone? Simple, easy question, good one. These are the mains level questions. Be careful there. Any doubts on this, please ask me. Clear? Let's see one more. We have a container. filled with liquid. Rho B, rho L, rho liquid is greater than rho B. Same story, everything is same. Here the pressure is P naught and this is X. Now what you did, you pumped air inside. Till pressure becomes 3P naught and then sealed. You sealed it, pressure became 3P naught. Everything is same, rho B, rho L, but the depth became Y. Compare X and Y. X greater than Y, X less than Y, X is equal to Y, can't say. Does the lighter ball move away? Yeah, because it is less denser than water, buoyant force will dominate, right? Another mains question. This is how the mains questions will be there. They will be a little tricky. They'll not ask you direct questions like medical means they'll ask you direct questions. They'll give you the formula and number, substitute and put it, they'll get the answer. Mains they will expect mains and bits, they'll expect you to think a bit. Okay. We have two answers, Vihan and Arush. Think, others. I'll give 30 seconds. Let's see. It's equal. The first of all, right, when you draw the FBD, buoyant force is equal to mg. Does the buoyant force change? It doesn't matter. That is one. Second argument. By Pascal's law, if you increase pressure at one point, it increases everywhere. So, by that argument, see what happens. If I draw the free body diagram with the pressure, what is the force here? P naught into pressure has increased, right? So 3P naught into L square. What is the pressure here? 3P naught plus rho liquid Gx into L square. It doesn't matter. That thing is going to cancel. And this is mg. So 3P naught plus rho L Gx L square. You can say, sir, pressure has increased, so it will push you down more. Agreed. But similarly, because the pressure has increased, the liquid will push you from the bottom also more. This was mg. So this pressure cut term will always cancel. No matter how much you increase the pressure, it won't matter there. And therefore, yeah, X would be same. The rho B by rho L into L. So X is equal to Y. Meaning I can call this Y axle if you want. Make sense? It doesn't matter. That's independent of the pressure. You increase at one point, it increases everywhere. So last time I was saying, right, Pascal's law, if you increase pressure at one point, it goes everywhere. It's actually used to make stuff, like this. If you ever seen these things now, when you want to make big spheres or big mirrors.
Video clip in various compilations.
So this is how they make spheres actually. You can see first they make this, whatever its shape is, this polygonal some structure. So they fill it with water inside, and the top, there is a dynamite, there is an explosive. See what happens.
YouTube, showing a small explosion going off inside of a polygon-shaped sphere, which forced it into a round sphere. The video usually...
You see what happened there. So think what happened, right? That explosive pressure, right, is so high, and by Pascal's law, the pressure is equally transmitted everywhere. So the whole, and the best shape you can get is a sphere, isn't it? If the pressure from one single point is going every direction, the shape you'll form is a sphere. And once you get these spheres, right, they empty the water, they cut it off, and they polish it. They make actually concave and convex mirrors.
What the objects were or what was happening, but I really wanted to know. So I started doing some research and found a company in China.
This is how they make spheres. If you haven't been to, this is there in Singapore actually. There are some places also. So they have these big spheres, meaning just a decoration items.
You make stainless steel spheres for art sculptures. The company,
or you can make big this concave mirrors and concave disc or solar panels and all that stuff. This is using nature to make spheres. If you try to manufacture them, there'll be some errors, but Pascal's law will give you pretty good spheres. That is one way you can say. So if you increase pressure at one point, it gets transmitted everywhere. Clear? Let's see one more. There. So if you see X is actually remaining constant every time, let's change that. So we have a liquid. Density of the liquid is rho L. Then we have gamma. Gamma is the coefficient of volume expansion. You kept a cube here. Rho B. Side L. Alpha is the coefficient of linear expansion of the cube. And this is X inside. So find a new X when the temperature changes by delta T. So if you increase the temperature, the liquid density will get messed up. The cube dimensions will get messed up. So a lot of things change. So find the new X. Get this. It's a good question. It could be a decent more than one choice question. Thermal expansion and fluid mechanics, everyone. Any ideas? Try. I'll give you another 1.5 minutes. It's a good one. Takes time. Little work, not tough though. Just give it a try. Get some water and come. Maybe on 3 alpha we won't get. This may, they can ask you like this also. Find the relation between alpha and gamma if x remains same. Puroza, that you got it. But that 1 plus square, you can do binomial approximation there because alpha is small. Then you are right. Because exam options may not get that square. They'll give you the binomial approximation one only. Because the logic is this. That 1 plus alpha delta t is derived under the assumption alpha delta t is small. So you can use binomial approximation. It works there. You have one answer, everyone. Jainil, that is wrong. You won't get 3 alpha, everyone. 3 alpha nahi aayega. It's not that apparent expansion wala nahi hai. Second more. Let's see. So first thing, let's see what are all the things that are changing. I keep asking this. Shana, you're right. So what all the things are changing? First thing, the density of the liquid changes. The rho nu will be the old density into 1 plus gamma delta t. That changes. Next thing, the side of the cube. Now this guy becomes L into 1 plus alpha delta t. So what doesn't change? What doesn't change? The mass of the block, right? Even if you increase the temperature, weight doesn't change. So now if you draw the FBD, that's it. It looks tough, but once you got this thing right, it is easy to solve. It is just one free-body diagram. You just have to be careful with what are all the things changing. So let this thing new depth be y inside. Let this be y. This is L into 1 plus alpha delta t. This is L into 1 plus alpha delta t. So we have the new buoyant force, which is the density of the new liquid, which is rho liquid by 1 plus gamma delta t. Liquid displaced y into L square 1 plus alpha delta t whole square into g. And you have your mg. Mg doesn't change, which is rho body into L cube into g, the initial weight. So equate them. The buoyant force is equal to mg, the rho liquid 1 plus gamma delta t y L square. That can be written as 1 plus 2 alpha delta t plus alpha square delta t square. We neglect this. Alpha delta t is small. This is rho b L cube g. You end up with y is equal to rho b by rho L into L 1 plus gamma delta t by 1 plus 2 alpha delta t, which is actually y is equal to x. X is rho b by rho L. This guy is x. 1 plus gamma delta t. They can also ask this in matrix matching. Meaning they'll give you conditions like this. Gamma is equal to 2 alpha. What is x? If gamma is less than 2 alpha, y will increase or decrease. Getting it? What is the condition if the block sinks more? What is the condition if the block, comes out of the liquid more? Like they can ask, they can frame some stuff like that. It's a decent result. It does it depend on 2 alpha, not on 3 alpha. You can further do binomial approximation and bring it up. This will be x into 1 plus gamma minus 2 alpha delta t. And you bring it up and then write as 1 minus 2 alpha delta t and multiply. That could be the answer. You have to be careful there, how they report the answer. most of the times I have seen they report the answer in this final form. So you will get till here and then you'll get confused what. Or sometimes you'll get this square and you'll not understand what to do. So be careful with that. When you see these thermal expansions, alpha, gammas, you can be sure like maximum you can use this Vanol approximation. Clear with this? Any doubts on the steps, please ask me. Clear? Next one. Any doubts? Devansh, Parth, Jainil, Kritik, Niharika, clear? Great. Daksha, clear na? Abhinav? So we have container here. Let's say we have a liquid, density rho1, height is h1. Then we have second liquid, density rho2, height h2. Then we have third liquid, density rho3. Now in this, you immersed a cylinder like this. This part is H3, not the complete thing, only that part which is inside. Outside pressure is P0, the area is A. It's in equilibrium. Find the bind force and the force due to the liquids. Find the bind force and the force due to liquids. JEE results are out today. Right? Mains first ka na? All the percentiles are given, ranks won't come now. Ranks will come after April 2nd attempt ke baad. People are blasting messages non-stop. I have 30 to 100 messages. I have to see after the class. I just saw few of them. I got like, there are few people did really well, few people messed up. I think there are so far 6 people who got 99 percentile and more. Let's see. Some people goofed up chemistry, some people goofed up maths, some people goofed up physics. So at least there's one guy who is happy, who thought he goofed up, but he did really well. His score is 199, but percentile is 99.55. Another guy got 237, and his percentile is 99.7 something. It depends on the shift also, na? Some shift it is tough, the scores are less. So people who got 180, they were feeling bad. But that shift was tough actually. And some other shift, people got 240, they're feeling happy. But the shift was easy. Meaning it so happened like this guy who got 180 and this guy who got 230, the percentiles are almost same. So that's what will happen. If the paper is tough, everyone will get smashed. In ionic equilibrium, na, chemistry, there's a concept called leveling effect. Did you study? So what leveling effect says is when you take a strong acid, when you take when you take a polar solvent like water, and if you put a strong acid like HCl or an acetic acid, which is a weak acid, both will behave like strong. So, but when you put them in benzene, the acetic acid will not work at all, but hydrochloric acid HCl will still work strong. So what it means is, philosophically, when the environment is good, right, or when the paper is easy, everyone will do well. Your true nature comes out when things are actually getting difficult. That's what leveling effect says philosophically. So when the environment is hard and then you perform, that is how it is. What is the answer for this? Anyone got it? Let's see. Now, if I try to draw the free body diagram for this, look at this. The first thing, the blue part, is pushing this way. So up to this part, it is there. Then comes the red one. That is still here. The green one. The green one is also pushing up. So if you look at the bind forces, now remember the bind force is simply the weight of the liquid displaced. So the first liquid F rho 1 is rho 1 area H1 into G. Make sense? Density of the liquid volume displaced into G. The bind force of the second liquid is rho 2 A H2 G. Bind force of the third liquid rho 3 A H3 G. That was easy. But if you ask for the force due to liquid, what is F1? Look at this thing. This F1 is pushing left and left, it cancels out. 0. The blue liquid is not exerting any force. Second liquid, 0. The red liquid is also cancelling out. There is only horizontal force. The green liquid is only the one who is exerting pressure here. So what is the pressure at the bottom here? The pressure here will be P naught, the top ka pressure, plus the blue liquid rho 1 GH1 plus rho 2 GH2 plus rho 3 GH3. That is the pressure at the bottom. So the force due to the third liquid will be P naught plus rho 1 GH1 rho 2 GH2 plus rho 3 GH3 into area. There. This is the force due to the liquid. This is what I was saying. The bind force due to the liquid and the force due to the liquid need not be same. The red and blue are exerting actually no force. They're cancelling out. So does that mean the red and the blue liquid are useless? Now this is where Archimedes will come and say, okay, they're not actually useless. This is what is happening. Listen, suppose if the blue liquid is not there, then this term rho 1 GH1 will be missing, right? If the blue liquid is not there, this rho 1 GH1 will be missing. If the red liquid is not there, then rho 2 GH2 atom will be missing. So what these two liquids are doing is they're not exerting the force directly, they're indirectly increasing the pressure at the bottom. That indirect pressure is pushing the whole system up. Are you getting it? So rho 1 and rho 2 are actually contributing for the bind, the net force, but indirectly. They're exerting their force through the green liquid. Is this making sense? And this is where Newton will come and say, I don't care. I will only care about the direct forces. You can help, from outside and that I don't care. You getting the difference? Whereas Archimedes will say, boss, the blue liquid, red liquid did contribute. I hope you're getting the difference between both. That's what I said. Bind force is completely experimental, whereas pressure part is completely theoretical. You can look at the answers, how different they are. But if you try to use an equilibrium, the final answer will come same. Any doubts on this? Have a look at this. It's a good one. Any doubts on this? This should make things clear. What is force due to liquid and what is bind force due to a liquid? Clear? Next one. Let's see one more. Take a break. Come back by 7:04. We'll continue from here. Any doubts so far? Chalo, come back in 10 minutes. Yeah, I'm sorry, everyone. I'll be busy today. So many calls. People who did well, they want to talk. People who messed up, they want to talk. Everyone wants to talk. I think at least 10 people across 99. Next year, it is your turn, everyone. Let's see. And the highlight is the one parent is confused. Sir, my kid got 93 percentile. Meaning, how can he get such a good score? Then I explaining the parent like, sir, 93 percentile, it's not percentage. Percentile is different, percentile is different. Each percentile is almost like 12,000 ranks or 10,000 ranks. So 93 is like 70,000 rank. Then the parent is like, oh, okay, then fine. Matlab, parent is happy now. So, nah, the parent was worried like, did this idiot copy and do some malpractice and got such a good percentage? So, parent was more worried about that. I didn't know whether to laugh or cry, but yeah, let's see. So then we have two liquids here. This liquid का density is rho. This liquid का density is 4 rho. We have a cube here, side L. Density is 2 rho. So X part is inside the blue liquid and the remaining L minus X is in the rho liquid. Find X. X is the depth of the block in 4 rho. Answers? This was easy. Let's see. L by 3 by 3. Cut off कुछ नहीं होगा रे अभी. After second attempt only you'll get the final rank. These are all just starting now. If someone improves this in the second time, they'll do better. They shouldn't be too happy about this because if someone improves, then your rank actually goes down. Think of like this. Let's say you got 99 percentile. So the student who got 98, next exam, if he gets 99.4, and if you improve this to 99.1, your rank has gone down by 1 unit, right? Because they'll take the best of it. So until the second thing gets over, we have no idea. So let's see. So there are two parts here. So there will be two bind forces. This is L minus X. So this bind force FB1 will be rho L square L minus X into G. The second bind force will be FB2, which is 4 rho L square XG. Your own weight mg will be 2 rho L cube G. Yeah, so the two bind forces FB1 plus FB2 will be mg. Rho L square GL minus X plus 4 rho L square xg is equal to 2 rho L cube G. So rho L square G, rho L square G, rho L square G. We get X is equal to, so this guy would be L minus X plus 4X is equal to 12. X is equal to L by 3. Clear? Basically, it can't sink into 4 rho. It can't float in rho. It will be stuck in the middle. Clear with this? Next one. Any doubts on this? You can do with pressure also. You'll get the same thing. But bind force is more easy. Now let's see that Archimedes ka thing. The story actually, how did he find the volume of the copper and that stuff? Yeah, this was a question taken from HCV. Let's get this. So we have an ornament weighing 36 grams in air, but in water it weighs only 34. So some copper is mixed with the gold. Specific gravity means what? 19.3 times the density of water. Copper is 8.9. Find how much copper is there. How do we do this thing? Just give it a try. Any ideas? Let's see. First of all, why did the weight decrease by 2 grams? That must be the bind force, right? So if you look at this, if the mass is 36 grams, right, and the bind force is 2 grams of water, So that is 2 grams weight. That is nothing but density of water, volume of the ornament into G. Rho of the water is 1 gram per cc. So from here you can clearly see volume of the ornament is 2 centimeter cube. So basically it displays 2 centimeter of water. So the buoyant force is 2 grams weight, which is 2 gram into G. G gets cancelled. There. So we know the volume of the ornament is V 2 centimeter cube. In that, let x grams be x centimeter cube be copper. Now, the mass of the ornament is density of gold into volume of gold, which is V minus x, plus density of copper into the volume of copper. Agreed? This is 36. I'll write everything in grams. So this is 19.3, and this is 2 minus x plus 8.9 into x. This is 33. This is 38.6 minus 19.3x plus 8.9x. How much is this? This is 38.6, 36, 2.6, 10.4x. X is 1 by 4 centimeter cube. Basically, out of 2 centimeter cube, 1/4 matlab almost 1/8 of the volume is copper. So if you want mass of copper, you can multiply 8.9 by 4 grams. I think that is close to 10.22 grams. Not 10.22, sorry, 2.22. That much copper is there. Easy. Next one. So this is how I actually figured out how much copper is there in the ornament without actually melting it or destroying it. Next one. We have a container. We have a hinge here and we have a rod here. Rod ka density is rho, length is L. Now what you did, you filled with some liquid here. Liquid ka density is 2 rho. That means the rod is trying to float. But what you did, you kept a hinge at the bottom so the rod cannot come out. And you poured a liquid of height L by 2. And this angle is theta. Find theta if the rod is in equilibrium. How do we do this? Yeah. How do you use torque? Well, how many forces are there on the rod? How many forces are there? Three. Hinge reaction, mg, buoyant force. Right, Ishana? Hinge reaction, you can say nx, ny, but okay, there is only one force. You can say hinge reaction two components. So if you say that, it is four. We have one answer. Shana got it. Others, you got a minute to draw the forces. So where does the bind force act? So bind force will act on this part ka center of mass, na? So start with an assumption. Let this be x. Calculate the bind force in terms of x. Draw the FBD. Calculate the torque about the hinge because you don't want hinge reaction. Get that? You got a minute. Let's see. Right, Nihayaka. Right, Daksha. We have three answers. So this was the rod. Let's say till here it is immersed in a liquid. Let this guy be X. The bind force will act somewhere here, FP, which is density of the liquid, 2 rho, area of cross section A, which I don't know, it'll get cancelled, X into G. This is your bind force. And how much is this? This is X by 2. Mg is acting somewhere here, and this length will be L by 2. Hinge reaction Ny and Nx. Nx is 0 anyway. I don't want to calculate that. So if you take this angle as theta, this is the bind force. This would be X by 2 sine theta. This is mg. This is L by 2 sine theta. Mg is nothing but density of the rod, area, length L, G. So torque about the hinge is 0 because it is in equilibrium. So mg ka torque is, so mg L by 2 sine theta must be bind force X by 2 sine theta. So actually theta cancels out. If I don't give the depth of the water, now you can't find theta. So theta goes off. This mg will be rho A L G. L by 2 sine theta goes off. This is 2 rho AX x by 2 sine theta goes off. Rho AG. You get x square is equal to L square by 2. X is equal to L by root 2. So the liquid is like this. This is L by 2. This is theta. This is L by root 2. Theta is 45. Is that clear, everyone? got this? Next one. Any doubts on this? So it's just based on torque. That is given in the question record. Clear? Clear, na, Nikhil, Devika, Ahana, Arush, Abhinav, Daksha, Daksha, you got it anyway. Sharman, Soham, Vihan, Ojas. What happened? Ojas tired today. You look exhausted. Next one. We have a solid cylinder with a cavity. So someone made a hole like this, meaning someone removed a scoop. So even this cavity, right, is filled with liquid. So this was mass M. This was height h. This was radius r. This is a solid cylinder with a hemispherical cavity at the bottom. So what I want you to find, in this cavity, also there is a liquid. If there is a liquid, the liquid is going to push this thing. Now remember, pressure is not constant here. This is the force on the curve, the curved surface. The cylinder ka radius is r and height is h. So find the force due to the liquid on the surface of the curved surface of the cavity. Find force due to liquid curved surface of the cavity. Are you getting what I'm asking? The liquid inside that cavity, there's liquid everywhere. So that will be pushing it. Remember, the pressure is not constant. Pressure is P naught plus rho gx. It is changing. You can't use the projected area. If pressure is constant, I could have directly said pressure into pi r square. How do we do this? Try. I'll give you 2 minutes. I'll tell you one thing, say. let's do one thing. Draw the FBD of this cylinder with buoyant force and draw another FBD of the cylinder with pressure. See, on the same FBD, you can't have both, right? So let's try to draw both of them separately. Do that, you will see something. So draw the FBD of this cylinder with the buoyant force. Draw the FBD of the cylinder with pressures. Because see, the moment you say force due to the liquid, aren't you talking about this pressure into this area ka thing? You're talking about pressures, right? So if you draw F curve, you can't use buoyant force in that FBD. So let's try to draw two FBDs and let's see what you will notice. Someone got minus 14 in max. Physics and chem he did well. He got physics and chem some 80 and 70. Max was a wipeout. Yeah, they're crying now. So let's focus on the class. I can't see your seniors crying now. Let's switch off. How to do this thing? Did you draw the FBD? Let's see. So tension, we are drawing FBD with buoyant force. Your own weight mg. Buoyant force will be density of the liquid. I think I forgot to give that. What is the volume? Cylinder will be pi r square h minus the cavity is 2 by 3 pi r cube g. Is that point clear, everyone? You should take the volume of the liquid displaced, isn't it? So even the cavity is filled with liquid, so you don't include that. Now same thing, if you draw FBD with pressure, this was tension. This was P naught into pi r square. You are mg. And the force due to the curve. Now, if you notice, I'm saying both the FBDs are one and the same. So tension, tension, fair enough. mg, mg, fair enough. So in place of FB, I have F curve and this thing, isn't it? And isn't that how we defined buoyant force as? Buoyant force is nothing but the difference in force between the lower and the upper surfaces. So from here, you can clearly see buoyant force will be mg minus t. And you can clearly see here F curve minus P naught pi r square is mg minus t. LHS is same. So the buoyant force is nothing but F curve. So there's no need to integrate in this. So comparing with buoyant force, you'll get this. So the force on that curved surface will be the buoyant force, which is rho liquid, pi r square h minus 2 by 3 pi r cube g plus p naught pi r square. Check. This is how you do if you have cavities inside the thing. Any doubts on this? Clear? Next one. You can actually try to integrate. That becomes more complex, but you'll get it. Any doubts on this? Kritik? Kritik? Clear? Vignajit? Kritik, not clear with this? Sharman? Soham? Ojas? Nikhil? Devika? Ahana? Ansh? Clear with this? Arnav? Jainil? Arush? Abhinav? Next one. This would be an advanced paragraph. Let's say we have a cylinder. Area A, density rho, height h. We have a liquid here. So you're dropping this from a height 3h. Gravity is there. And the density of the liquid is 3 rho. So what will happen? This will fall into the liquid, but liquid is more denser, so it will slow down, stop, and then again it will come out. Getting it? So the first question is find the maximum depth the cylinder goes into the liquid. Now I can ask you the time also, but that requires SHM. We will see that later on. But approximately plot acceleration versus time graph. Or approximately plot. Yeah, approximately, no, you can plot actually AX graph. Plot AX graph, acceleration versus position graph. Even AT graph would have looked same, but okay. Let's get this. This is a good one. I'll give 3-4 minutes. This will be an advanced paragraph one. First, try to figure out what are all the steps in the problem. Think, take a minute or two, then I'll show you something, then I'll give another 2 minutes. Let me show you the scenario, what is happening here. See, this whole thing consists of three main parts. The cylinder falling in the air. So just before hitting the water, this is the scenario. So your speed will be v1. Then after hitting the water, you will be entering the water. Means you'll be, some part will be inside, some part will be outside. Then you will completely enter the water. By then you must have reached a speed v2. And then you will travel inside the water and finally stop. The initial velocity 0, final velocity 0. You must have reached a depth y. So there are three parts in the problem: falling in the air, while entering the water, and inside the water. So while entering the water is the main part. While entering the water, the buoyant force is changing with x. You get a variable acceleration. Did you integrate? Now try. You can find v1, that is easy. Maybe that's not the answer. Conservation, what are you exactly conserving? Then you should take work done by buoyant force also. Isn't buoyant force an external force on the system? Is it constant? See, the problem I बोला ना, while falling problem नहीं है, while entering problem नहीं है. The headache was this one. While entering, your buoyant force is variable. You have to integrate for that. Yeah. Conservation you can use, but then you have to calculate work done by buoyant force. Integration तो लगेगा ही. Now try. I'll give you a minute or two. So for the first part, what is v1? That is easy. We are using the equation v square minus u square is 2s because gravity, it is constant. So we get v1 square will be 2g. This is 3h, everyone. So v1 is root over 60h. So hit the water with this speed. At this instant, what are the forces? Buoyant force will be density of the liquid, which is 3 rho, area, x, g. Your weight is mg, acceleration. So we get mg minus 3 rho a xg is equal to ma. Mass will be rho a h g minus 3 rho a xg. Mass will be rho a h a. So rho a will cancel. Acceleration will be g into 1 minus 3x by h. There, that's your acceleration, which is variable. You have to integrate this. So v dv by dx is equal to g into 1 minus 3x by h. So this is the situation while entering the water. v dv limits will go from v1 to v2. So just before entering it is v1. After completely entering it is v2. G limits will be integral 1 minus 3x by h dx. Limits will go from 0 to h. This guy will be v2 square minus v1 square. This will be g into h minus 3 by h square by 2. v2 square, v1 square is 6gh. That would be g into minus gh by 2. So v2 square Goofed up something here. I goofed up. There is a 2 here. That would be 5GH. There. So when you enter the water, you will have this speed. Check out the steps. Now, once you enter the water, your life is again easy because acceleration becomes constant. So if A is constant, you can use the 3 kinematics equations. The headache is while entering. And if they ask you time, meaning if it is an advanced paragraph, I'll ask you time and ask the depth. Done. These two will kill you. That would be a really good advanced problem because this time you can calculate, this time you can calculate, this will be SHM. I'll teach you this in harmonic oscillations that you can't calculate directly. Any doubts on this page? So once you completely enter, I'll turn the page. So once you are completely in, you are bind force. Now it has become constant. 3 rho AHG. mg will be rho AHG. Acceleration will be up. FB minus mg is ma. 3 rho AHG minus rho AHG is equal to rho AHA. K is equal to 2g. So it's actually decelerating with 2g. So your speed will be v square minus u square is 2as. Your final speed is 0. Initial speed is 5gh. This is minus 2g and this is some y. Y is equal to 5h by 4. Meaning after completely entering from this position, you have gone 5h by 4 further. So matlab the total depth you would have gone would be 5h by 4 plus h. That would be around 9h by 4. Depending on which surface you are measuring. So if you take the topmost part, it will be 2h plus 5h by 4. Is that clear, everyone? Because the displacement starts from here. Once you completely enter from here to here, actually that is, I can take this actually, that is also fine. This is 5h by 4. Same thing. Plus h will come if you take the top surface, bottom surface. Are the steps clear, everyone? So there are 3 parts to the problem. And how will the graph look like? If you plot A versus X graph, let's take down as positive, up as negative. Initially, the acceleration will be like this. Constant minus g. This is in air. This is the motion in air. Then if you see your acceleration was 1 minus 3x by h. This is a linear function y is equal to mx. This will go till plus 2g. This is till you enter the water. Once you enter the water, it will become constant for some time. This is while entering. This is inside water. And then again, you'll start coming out. This is while coming out. Then again, you will fly in the air. This graph will never stop. This particle will never stop. Again, it will go. This will just keep on going. You're getting it's a repetitive graph. Is this making sense, everyone? So this graph will just keep on going. If there is no viscosity, this thing will never stop. The cylinder will just keep on flying up and down non-stop. That's how the AX graph would look like. So there are 3 parts of the problem. You're in the air while entering and inside the water. The headache is the entering part. Because it is a cylinder, you can do it. If it is a sphere, you will die. Sphere is a mess. Because imagine like this. If a sphere is entering like this, how will you find this volume? You won't get a linear function. It won't be so easy to solve. Clear everyone?
सर
हाँ देवांश.
सर प्रीवियस पेज पे एक बार सर यहाँ पे v2 स्क्वायर माइनस v1 स्क्वायर बाय 2 रहना चाहिए ना.
Did you find the 2?
हाँ.
I did that. लिखा था मैंने. First I forgot, then I wrote it. Clear? Next one. This is a good one. This would be a good paragraph question. Let's say we have some water. Inside you kept an ice cube. Density of ice is 0.9 gram per cc. Case 1. This is pure water, which is 1 gram per cc. Remember, whenever you melt ice, you get pure water. Case 2, someone mixed the water with some alcohol. So the ice is floating in water plus some alcohol, which is 0.95 gram per cc. Case 3, someone mixed a lot of salt. So the ice block is floating in a salt water. The density is 1.05 gram per cc. 3 scenarios. Now, if the ice block melts completely, what will happen to the liquid level? Remember, whenever ice melts, you always get pure water. So if ice melts completely, what happens to the water level? Increase, decrease, remain same. Again, another decent question. The first one is the standard one. Second and third I made up. Let's get this. I'll give you a minute. It's an easy one. Let's see. First of all, so when you put this ice in the water, let's see the how much is it inside. This was x. This we just calculated. X is nothing but density of the block by density of the liquid into L. Right? So that is the thing. Next thing, what happens if this ice melts? So when this guy melts into water, what remains same? The mass, isn't it? Mass of ice is equal to mass of water. So this is 0.9 volume of ice is 1 gram per cc volume of water. That means whenever this will be 0.9 L cube. So whenever the ice melts, you get only 90% of the water. Clear? Now, case 1. Density of water is 1 gram per cc. Therefore, we'll get x is equal to 0.9 L. That means if you remove the ice cube, you will see that cavity which you get, this volume will be exactly 0.9 L cube. Agreed? Getting it? So if you have pure water, the volume you are creating is exactly 0.9 L cube. So this volume will be 0.9 L cube, the volume of the cavity. And how much water do you have? You have 0.9 L cube. So you're taking and putting it in this. So what will happen? It will exactly fill the cavity, right? So it will remain same. Is that making sense? So if a pure ice, right, which is floating in the pure water, if it melts, it's not going to change the water level. Second case, when the rho of the water is 0.95 gram per cc, x will be less than 0.9 L. So volume of the cavity is less than 0.9 L cube. I wrote reverse. X is greater than 0.9 L. Meaning, up logically, socho na, if the density is less, shouldn't the ice sink more into the water? If you're putting ice in a less denser water, it will sink more. So that means this cavity which you get will be greater than 0.9 L cube. But how much water you have? You still have 0.9 L cube. So if you put it here, what will happen? It will not fill the cavity completely. So water level will decrease. Is the logic making sense, everyone? Whenever the ice melts, you always get pure water of 0.9 L cube. So the problem here is this: when you put it in a pure water, your cavity is 0.9 L cube. Water is also 0.9 L cube. Everything is great. When you put it in a water plus alcohol, density is less, so you have to sink more. Cavity is bigger. When you put it in a seawater, the density of ice is more. Density of the water is more. So cavity will be smaller. You need not sink more. So x is less than 0.9 L. So volume of the cavity is 0.9 L cube. So this cavity will be smaller, but you still have 0.9 L cube water. And you're going to put this water here. So what will happen? It's going to overflow. Increase. Is this making sense, everyone? So the three cases, the cavity ka or the volume displaced is not same. But every time you melt, you always get 0.9 L cube. Any doubts on this? All clear with this? Clear, na, Vihan? Soham? Puroja? Arya? Clear? Nikhil? Sharman? Parth? Got this? Jainil? Next one. We have a container here. We have a wooden block here. Maybe a wooden plank or something. It is floating. On top of this, you have a cylinder or a block. You throw this into the water. So we have here, this is X. We have here, this is Y. So X is the depth of the block inside the liquid. And Y is the height of the liquid. Case 1, density of the block is greater than density of the liquid. Think of like this. We have stones on the boat and we have water. Case 2, density of the body is less than density of the water. Maybe you have thermocol sheets and you have water. Are you getting the catch? So in case 1, you throwed stones from the boat into the water. Case 2, you throwed thermocol sheets from the boat into the water. If block is thrown into the water, what happens to X and Y? So 2 problems, 2 cases. Let's get this. Last one for the day. Let's finish it off. X is easy. Isn't X easy? If you take the weight away from the block, what will happen to the block? Will it sink more? Will it come out or will it stay there? It will come out a bit, right? Because the boat need not support the weight of the, the plank need not support the weight of the block. The X will decrease a bit, isn't it? X is easy. Whether rho b is greater than L or rho b less than L, both the cases X will decrease. Y is interesting. Okay, what about the second one? Maybe second is wrong. Think I'll give you a minute more. You saw today we saw a lot of theoretical type of questions. नहीं बोलो जा. Both the cases नहीं होगा. So if you see the first part, so this block का weight mg, this is mg. This bind force will be rho liquid AXG. So FP is m plus mg. So rho liquid AXG is equal to m plus mg. So if small m is removed, X will decrease independent of density. And that was easy. Second is a twist. Right, Ahana, you got it. No, Ahana, first case is wrong. Interestingly, you got the first one messed up. Now look at the second one. Case 1, the density of the body is greater than density of the liquid. So if you want to float, the bind force must be equal to mg. What is the bind force? Density of the liquid, volume displaced into g, density of the block, volume of the body into g. The volume displaced will be rho b by rho l, volume of the body. You can clearly see this is greater than volume of the body. So when the body or the block is on the plank, look at this thing. So in order for the block to float, you need to displace more water. I'll give you some numbers. See, let's say density of the block is 10 times water. Let's say we have stones there. Stone ka density 10 times water. What is the meaning of this? To float one stone, let's say if you have this much stone, to float this one stone, I need to displace 10 times the volume of the stone, right? Isn't that the meaning of that? Because in order to float, the buoyant force, the weight displaced of the water must be equal to the weight of the stone. So when you say density of the stone is 10 times, iska matlab ye hai, you need to displace 10 times the water, 10 times the volume of the stone. Is that fair enough? But if I throw the stone into the water, how much will it displace? One stone will displace only one volume, right? So did you see what happened there? When you're on the boat, you're displacing 10V, but when you're in the water, you're displacing 1V. So baki 9V kahan pe gaya? It will decrease, right? Is that making sense? If you jump from the boat into the water, boat will come out, water level will go down. Isn't it? So when block is on the plank, the volume displaced, so you're displacing more water, is greater than volume of the block. So when the block is in the water, it will sink because it cannot float by itself. And volume displaced becomes equal to volume of the block. So now you tell me, in which case did the volume displaced was more? In the first case, right? So when you throw the stone into the water, the volume level will go down again. Is that making sense? Think about it. Therefore, y decreases. It's a good one. Meaning, I'll give you an example. Listen. Let's say we have a boat. Okay. This is the water level. Now, let's say there are stones here in the water. Now, if you take this stone and put it in the boat, boat ka kya hoga? Boat will go down. Agreed? In this process, what will happen to the water level? Will go up. Everyone agrees with this thing? Now, question starts from here. If I take the stones here and put them back in the water, won't the boat come up and the water level go down? Now you agree? So the question is saying the stones are already there on the boat. Now if I put them back in the water, what will happen? Is this clear, everyone? The question starts from the stones are already in the boat. If I put them back in the water, what will happen? It will go back to that initial level. Sure. Means which is decreased, right? So if you put the stones from the water into the boat, water level will rise. If you put the stone back into the water level will decrease. I hope that was clear. This is a mathematical proof, but yeah. So y decreases, x also decreases. The second one is interesting. Tell me one thing, if you take thermocol, if you put it in the water or if you put it on the boat, it can float by itself, right? So if it can float by itself, it will always displace the same water. So to float, FB is equal to mg. We get rho liquid, volume displaced. G is equal to rho body, volume body, G. We get volume displaced is rho B by rho L VB, right? Now, if you throw into the water, the buoyant force is equal to mg because it floats. That means you still get Vd is equal to rho B by rho L into Vb. So there is no change in volume. Means whether you put me on the boat or put me in the water, I'm going to float. So I'm going to displace the same amount of water. No change in displaced volume. So the volume will remain same. So simply this is how you can remember. If something can float by itself, you put that on the boat or you throw into the water, it will be the same. Again, let me give an example. Let's say we have the boat here. We have a wooden block here floating. Let's say the block ka density is half of water. Iska matlab kya tha? It will just displace half of the volume to float, isn't it? So when this guy is on the boat, how much will the boat displace water? V by 2. If I throw this into the water, how much will the block displace? V by 2. It is the same, right? What happened with the stone? Because the stone ka density was more, the boat was displacing more water for you. But for a wood, the boat will still displace the same amount of water, which the wood could have displaced on its own. I hope you're getting the difference. So when you drop something more denser, the boat will displace more water to compensate, to lift you. So the water level rises. When you put it back, it decreases. But for lighter objects, it doesn't matter whether you keep in the boat or in the water. Think about this. It's a pretty good question. Not tough, but theoretical. Most people will go for the second part. Think about this. If you're still confused, ask me in the next class. So this is again there. It's all buoyant force. If you actually observe, today we did only with one concept. Buoyant force is rho liquid V displaced into G. We just played around with that. We did almost 10 questions. Fluid statics part is mostly done. Maybe we'll do 1 or 2 more questions in the next class, and then we'll start off with the fluid dynamics part. So far, if you observe, liquids have not moved. Now liquids will start moving. That is not that tough. It is still fine. We have some decent questions on that also. Okay, with that, we'll wrap up for the day.